And who just came? Huda and Amna. Okay. Okay. Now let's roll. So, speaking of this, then. Oh my God. Right. So, we're gonna basically start with this topic, which is called influence of one conductor on another conductor. So let's put that heading here. Let's see. All right. So remember, in IGCSEs, we learned that like currents attract and unlike currents repel. This is what we learned. If you remember, when the wires would be taking like current in the same direction, like this, you would then see that they would have an attractive force between them. And when the wires were taking current in opposite direction, they would have the opposite effect. They would repel each other. So we're going to see why this would happen and through some examples. Okay. So first off, let's do an example here. So, oh, we don't have the size. Okay, I'm gonna go to the next page. You can quickly copy this, please. Okay, now, so going to the next, please. Have a look here. So let's do an example. So there's a wire. Oh no, a straight wire like this, and it's taking a current of I1 of 6 ampere like this. Now, there is another wire which is right here, which is basically taking a current of 4.8 ampere. So let's call this I2. We also know that the length of this wire is 1.2 meters. All right. Now, obviously, one wire's field is going to affect the field of the other wire. So we're going to look at what happens to wire 2 at this point X when they have a separation between these two of 2 centimeters. Do you guys understand what I'm saying?
Yes.
Okay. First of all, we must understand that it has certain steps. Okay, wait. My house is like my office has some things going on. Wait. So let's write step 1, please. Step 1 is that we always find magnetic field strength at point where it interacts with other wire.
Define the point X.
Second, please. Always find magnetic field strength at point where it interacts with the other wire. Is it clear?
So in this case, point X.
This it is point X, yes. Because this is a circular field, so we're going to use B equals to mu naught I over 2 pi r. Find this. So now let's have a look. So the B at X is going to be mu naught, which is 4 pi times 10 raised to power minus 7. I told you to remember this. This is 6 ampere. Because of this the field is of the 6 ampere wire divided by, obviously, the radius of this circle will be 2 centimeters. So we're going to write 2 pi into 2 into 10 raised to minus 2. Understood?
Yes.
Now this will give us basically the strength of magnetic field at that particular point. So that's the strength of that magnetic field. Now let's have a look at the other wire. Now step 2, find the force acting on other wire. So how do you do that? Very simple. You're going to use F equals to BIL. This is what you're going to do. So force, the magnetic field that's affecting that point is 6 into 10 raised to minus 5. The current that it has is 4.8. And the effective length of that wire is 1.2 that we have been given. So this will be 3.46 times 10 raised to power minus 4 newtons. Is it clear? Now also, in some questions, they will ask you to find the direction of this force. So step 3, find the direction of force using Fleming's left hand rule. For that to work, first of all, we need to see where the direction of field is. So according to my right hand grip rule, the direction of the field has to be this way. You guys agree? Basically anti-clockwise, huh?
Yes.
So if I look at point X right here, the field is coming out of the plane or page. So we're gonna say, if you look at the wire like this, so this is wire, and the field is just coming, basically it's pointing out of the page, so I'm gonna put a dot. Is it clear, everyone?
Yes.
And the direction of current in this one is upwards with 4.8 ampere as the direction. So now you can use the left hand rule. Your index finger should come out of the page. Your middle should go up. So you will see that your thumb is pointing towards the right. So which means at X, this wire is going to have a force towards the right. So I'm going to say forces to the right. Now, the conclusion for this is that then you should also understand, I'm just going to change the color to write this down. And this part, we're going to see that due to Newton's third law, when wire I1 exerts a force on I2, I2 exerts equal and opposite force on I1. So due to Newton's third law, where wire 1 exerts a force on I2, I2 exerts equal and opposite force on I1, which means that these two forces will be equal and opposite. Do you know what this means? This means that these two wires are going to attract each other. Is it clear?
Yes.
So you guys can basically write this down and do let me know if you have a question. Right, kids, everything is clear. Should I go forward now?
Yes.
Okay. Now, the next. So, in another example like that, oh my god, had to start it this time. Wait a second. This recording is ruined, by the way. That's okay. Chalo, never mind. So now we're going to look at example 2. So in example 2, there is one wire that goes like this. There is another wire that goes like this. One wire takes the current basically upwards with 3 ampere, and this wire is infinitely long. Then the other wire basically takes the current this way, and this wire has a current of 4.8 amperes. And the length of this wire is given as 3.2 meters. Okay. Now, the distance between these two wires is given as 0.25 centimeters. Right? Now, I just want you guys to try this at least and give me the answer for the force and the direction of the.
Won't the magnitude be infinity?
No.
Now we need to find the force on which wire? On the 3 ampere one or for 8.8 ampere one?
According to Newton's third law, it will be same on both. So it's up to you. You got to pick and choose in this. Which one do you think is suitable? Fine.
Alright, 4.81.
Yes, obviously, because the length is given for that. Okay. Okay, quickly do this. This is like 2 minutes thing. Till my office thing will be fixed as well. Okay, kids, you got an answer? Nobody got an answer. This is very bad. Okay, now, so Samir, what is this? No one responded. Samir, the link has. Okay. All right. So now check this one. So first step is that you always draw the field. Okay. So I'm gonna draw, because I don't have the length for infinitely long wire. I'm gonna draw the field of this first. So I'm gonna draw it like this. So this one will also be anti-clockwise. Just draw it till it reaches here. So okay. So basically it goes like this, like that. Okay. Now let me just draw it nicely. It should come out like this. Should go like this. Okay, now it seems better. So it's this point we're looking at. Write this. Now, first of all, again, step one. Step one is that you basically find the magnetic field strength, which is B equals to mu naught I over 2 pi R. So then obviously the magnetic field at this point, let's call this Y this time, okay? So magnetic field at Y is going to be 4 pi times 10 raised to minus 7. The current is the current in the wire is 3 ampere. Because we're looking at the field of 3 ampere, so we're going to put 3 here, divided by 2 pi, and the radius of this is 0.25 times 10 raised to minus 2. This should give you an answer of 2.40 times 10 raised to power minus 4 Tesla. Everybody got this? At least?
Yes.
Yes.
Then we are gonna basically go to the step 2, where we got to find the force on the wire that we have the field going through. Okay. So we're gonna use the formula F equals to BI/L. We already know that the force in this, force at Y, is going to be B is 2.40 times 10 raised to power minus 4. The current in that is 4.8 and the length is 3.2. So the total, the value of this should be 3.69 times 10 raised to power minus 3 newtons, like that. Obviously, this force will be equal in magnitude for the other wire as well. But I just want to put a note here so you guys do not forget. Remember that only the overlapping length is considered. Even if we had taken this wire in consideration, we'd still use this length because these are the two lengths. This is the length that is overlapping. We can't take any other length. We can't take infinitely long lengths. Is it clear, everyone?
Yes.
Yes.
Now, if you look at the direction of the field, it is basically going into the page, which means in step 3, for my reference, if you don't want to do that, you don't have to do it. But for my reference, the wire is like that, and the field is basically going into the page there. So it means it will be across, like that. Okay. Now you can use the Fleming's left-hand rule. Your index finger should go into the page, middle down. So you'll notice that the force on this wire will be on the right as well. Can you check, please? Which also means that the force on the other wire will be on the opposite direction. So if this basically applies a force on this wire to the left, the force on the other wire will also be, towards the right, it will be towards the right as well. Left, opposite. So equal and opposite forces will act. If one wire acts on the left, then the other one is going to act the force of the same value on the right. Is it clear, everyone?
Yes.
This is force to the right. Earlier, I basically drew it correctly, but then did not say that it's right. I said left. Sorry for that. So you can basically copy this question is only this much. I mean, if you just follow these 3 steps, I don't think so you will ever get this wrong.
Sir, at the end of the lesson, can you send the link for these notes again? I wanted to check a few things from previous chapters, but I couldn't open the link you uploaded on Google Classroom.
This link, the notebook link,
Yeah.
yeah, sure, why not? I can do that.
Sure.
Okay. Should I go forward now?
Yes.
All right. So in fact, we can basically draw combined field of these 2 examples. First example, so let's write net magnetic field. And from this one, I'm just going to say if there are 2 wires, in fact, let me just draw that first. So there is a plane we're looking at. Like that. And then let's draw another plane, or why not just copy it. So the first example was when there were 2 wires, those were carrying current. In the same direction. So what happens is that the field, if you draw the field from right hand grip rule, the field of this one goes like that. The field of this one also goes like that. These are similar fields, but when you look at the center of these, they basically are opposites. So because you see at this point, the arrows are like one is down, one is up. So that's basically opposite fields. So they certainly attract each other. So the net field is drawn like this. It basically shows you a shape like this, by the way. And that can be done through a compass. Well, that's not required for you to know. But at the center of this, right here, there is literally nothing. There becomes a null point here. Okay. And the reason why this happens, because they're opposite to each other. So at this point, we can say cancellation of magnetic fields take place at the center. Like that. On the flip side, when we look at this one, when you have 2 wires, which are taking current in the opposite directions. So what happens is when you do the grip thing, the field is going to go like this. This field is going to go like this as well. So in the center, they have similar fields. So what happens is that these fields basically do not connect because they repel each other. And they sort of create a design like this. Okay. So you can draw this, please. So this we have done in IT as well, so it's not something to worry about. Now, in recent papers, I remember, I think it was 23 probably or 22 October, November. While you draw this, let me check. There was a question that sparked my interest. Wait a second. We're going to do that thing here as well because now I know that that can also come. Cross papers. Interesting. Certainly not in May, June. March 42. Well, well. Okay, never mind. I'll look for it. Just a recent question. So should I go forward now? You guys have drawn this?
Yes.
Okay.
Yes.
Basically, I read about it, and basically these are called the bed springs. So a bed spring basically looks like, oh my god,
The
these,
same bed springs in our mattresses.
yeah. That's why they're called bed springs. Okay, kids, like this. Is it clear?
Yes.
Now, in that question, they had given a couple of things about these. First of all, they said that the radius of these are 4 centimeter, and the length between these two springs from center to center is 2 centimeter. Is it clear?
Yes.
If the current is passing through them at 8 ampere, so obviously the current goes like then this, and it basically circulates around it and then goes like that. Get it? Now, they say that the bed spring will twitch. It's gonna move. Okay. Now, because currents are in the same direction. Now, a lot of people, I think they got it wrong, but now I'm going to tell you why. Because nobody ever taught this before, so that's fine. Anyway, let's look at this. If you basically slice them from this point to this point, so actually, and you when you look at from the front, they basically seem like that there are two wires that are arranged parallel to each other like that. Do you understand that?
Yes.
They run actually parallel to each other, which means if there was an 8 current, so obviously 8 ampere would be in this, and 8 ampere is within this as well because this current is circulating. And when you basically try to take the field of one wire, the field generated by one wire is going to affect the other wire like this. Do you get it? So this is the magnetic field. Understood?
Yes.
Naturally, this distance between these two would be about 2 centimeter, and the effective length between these two is going to be, if you just look at the whole thing, the effective length between them will be about 8 centimeter because it's the radius, right? Do you get it?
Yes.
Yes.
The rest of the things are the same. In fact, my bad, it's not 8 centimeter. The length would be equal to 2 pi r because we have to take all this the circular circumference actually. Do you guys get it? Because the actual wire is like this, now. Actual wire is like this. It's a spring. So which means that the perimeter of a circle is 2 pi r. That's why we need to take this length. So this is something you guys need to remember. Understood?
Yes.
Yes.
Okay. Rest of things are the same thing. First, use B equals to mu naught I over 2 pi r to find B. Then use F equals to BIL to find force on one of the wire. And then the last thing is that lastly, force will be equal and opposite. So because they're carrying current in the same direction, so they will become, so they will reduce their separation because this will be an attractive force. Understood?
Yes.
If you want to find the direction can be found using Fleming's left hand rule. Just write this down because I don't think so. 90% of people have not done the papers and they're not teaching this, which is very sad. So you do this, please. Okay, so considering the situation, I just want to tell you that they might also try to give you a question which is sort of rectangular coil. Okay, so I'm just gonna put that for the reference. I think that question came in 2022. So just write alternate question. In an alternate question, they might give you a coil which looks like this. Okay, so if they give you a coil like this, so then you have to take the perimeter by adding the four lengths. Maybe the lengths might be different. So it's going to be 2L plus W for the total length. Is it clear, everyone?
Yes.
And this sort of question might also have a bit of strange thing going on. Current is going like this, would be a coil like this, okay, like that. It keeps,
Basically, that single coil type in the generators.
yeah, something like this. It would be like this. I can't exactly recreate the 3D thing. My drawing is super bad. But then I just want to tell you, if the current goes into this, it will go like this. And then obviously the current will be opposite on the parallel side. So you need to basically know what kind of force and the direction is going to act there. Is it clear?
Yes.
Yes,
Yeah.
sir.
This is an alternate question. If you, I'm really short of time now, but I wanted to do that question. But hopefully, I'll give you that question as an assignment, or probably do it in the class next time. All right. So see you then. Have a
All
nice
right,
day.
sir.
Bye.
Sir, could you send the